So in digital electronics, divided into two concepts. One is combinational circuits and sequential circuits. So in sequential circuits, flip-flop plays a major role or the fundamental blocks in sequential circuits. So a flip-flop in digital electronics is a circuit with two stable states that can be used to store binary data. So flip-flop is used to store the binary data, and flip-flop is a one-bit storage element, and these are fundamental building blocks of digital electronics. So in computers, communications, everywhere we are using flip-flops. The primary difference between a latch and flip-flop is a gating or clocking mechanism. So flip-flops are edge-triggered one, and whereas latches are level-triggered one. So in this video, we will see flip-flops. There are four types of flip-flops in digital electronics: SR flip-flop, JK flip-flop, D flip-flop, and T flip-flop. First one is SR latch. Flip-flops are built from SR latches. SR latch using two NOR gates. This simple circuit has two inputs S and R. S is set, R represents reset. Here we are using two NOR gates. So first NOR gate output is input for the second NOR gate, and similarly second output is input for the first one, and two outputs are Qn and Qn bar. This is the logic symbol. So when inputs for different combinations of inputs, and if the present state is 0 or 1 depending on the present state, next state will be present. If inputs are 0 0, if both inputs are 0 0 for the given NOR logic, so if present state is 0, output is also 0. If present state is 1, output or next state is also 1. Nothing but when two inputs are 0 0, next state is nothing but equal to the present state, that is Qn plus 1 equal to Qn. So next coming to the different inputs 0 and 1. So 0 1. So if inputs are 0 1, whatever the present state, output is 1, that is nothing but state. And coming to another combination 1 0, if inputs are 1 0, whatever the present state 0 or 1, whatever the present state, output is 0, that is reset. Now when both inputs are 1 1, whatever the present state, either that is 0 or 1, output is indeterminate state, that is nothing but toggling state. So this is the simplified truth table for the SR latch using NOR gates. So inputs are 0 0, what are the present state? What are the present state? Output is Qn, that is nothing but hold state or previous state. Similarly 0 1, whatever the present state, output is 1. Similarly for 1 0 0 and 1 1, indeterminate state. Next is same SR latch using two NAND gates. Same in place of NOR gates, you will observe NAND gates. Same one. So we will see reduced truth table. So when S and R both are 0 0, indeterminate state. Okay. When 0 1 1 and 1 0, what are the present state? You will get 0 1 1 Qn. If you want compare both the truth tables with NAND gates and with NOR gates, so two tables are exactly opposite for the input combinations. If 0 0 1 1 interchange and 0 1 1 0 are interchanged. So now construction of SR flip-flop by using NOR latch. So here we are using NOR latch, and two input gates are AND gates. This is SR flip-flop. So here we are applying clock pulse. This is SR flip-flop. This is the logic symbol for flip-flop. Similarly using NAND latch. So the truth table, we will say simplified truth table. If present state is 0 0, if present state is 0 0, and whatever the present inputs are 0 0 and present state is don't care, nothing but 0 or 1, so output is indeterminate state. For 0 1 combination, output is 1, that is nothing but set state. Similarly for 1 0, S is 1, R is 0, reset state, and 1 1 is hold state, S equal to R equal to 1. Okay. So this is for one second flip-flop. For the first flip-flop, the truth table is 0 0 0 1. Okay. Same for 0 1 0 1 0 1 and 1 1 indeterminate state. So characteristic equation is nothing but finding the Qn plus 1 equation, output equation or next state equation in terms of inputs and present state. So consider Qn plus 1 equal to 1 combinations and place in the K map. Here we are using, so we consider inputs, nothing but inputs are 3 or output or next state depends on 3 variables, that is S, R and Qn. So now take 3 input K map and place once, and by after grouping, the expression is Qn plus 1 equal to S plus Qn into R bar. This is the characteristic equation. So next is excitation table. So excitation table is nothing but for a given combination of present state Qn and next state Qn plus 1, excitation table tells the inputs required. So very interesting point is when you are comparing truth table and excitation table. So truth table is when we are giving inputs and if you know present state, what will be the output. So finding output is in truth table, whereas in excitation table, finding inputs for present state to next state. Suppose if present state is 0, I want next state is also 0. So then what inputs I have to apply? So in the same way, other combinations. So this is the excitation table for SR flip-flop. Okay. So if present state is 0, next state is 1. I want 1, then SR should be 1, 0. Okay. This is excitation table. So next one is the JK flip-flop. So JK flip-flop. Okay, here we are having one more input, one more clock pulse JK and one more input to the NAND gate. This is output of the second gate or QN bar. QN is connected to the K gate, whereas J gate is from the QN bar. This is the logic symbol. So this is the truth table of JK flip flop. So when J is 0, K is 0, hold state. When J is 0, K is 1, reset. When J is 1, K is 0, set state. And similarly, when both are ones, toggle state condition. So Qn plus 1 equal to Qn bar. Whereas in SR flip flop, when both inputs are 1, generally consider condition is indeterminate state. But in JK flip flop, we can eliminate that state and when J equal to K equal to 1, Qn plus 1 equal to Qn bar. So characteristic equation of JK flip flop similar to SR flip flop. So take the Qn plus 1 equal to 1 combination for J, K and Qn bar, place in the K map and grouping. Here you are getting two pairs. So two pairs and this is the characteristic equation of JK flip flop. So this is the excitation table. Next is the D flip flop. So D flip flop is also called delay flip flop. So this delay flip flop is we can design delay flip flop from SR flip flop only simply by placing one NOT gate in between S. This is S and R. SR in between S and R. If you place one NOT gate, this will act like a D flip flop. So in D flip flop, output is equal to the input. So that's the reason it is called a delay or data flip flop. So this D flip flop most widely used for counter shift registers and for input synchronization. So we can observe. So whatever the D, you will get Q. Next is the T flip flop. T flip flop is like a JK flip flop, or from JK flip flop we can get the T flip flop. So when J equal to K equal to, if you make J and K are tied together and the resultant terminal is T is a toggle flip flop. So if you once observe the table when T is 0, Qn plus 1 equal to Qn. When T is 1, Qn plus 1 equal to Qn bar. We can observe when T is 0, Qn plus 1 equal to Qn. Okay, when T is 1, Qn plus 1 equal to Qn bar. So this is about T flip flop or toggle flip flop. Thank you.